Okay, today we are very happy to have Hsi-Yu, who is joining us from Taiwan. He's giving a talk at a very inconvenient time in his time zone, so thanks to him. And he's going to tell us about Brownian motion of FDM solitons. Hsi-Yu.
Okay, thank you. Thanks for the introduction. And it's also my pleasure to be able to attend this virtual fuzzy dark matter workshop. So I'm Schive from the National Taiwan University, and today I will talk about this Brownian motion of fuzzy dark matter solitons. So this is outline of my talk. First, I will briefly introduce this fuzzy dark matter, FDM, and then I will talk about some challenges in these fuzzy dark matter simulations. And finally, I want to focus on this soliton random walk. So first, a brief introduction. So I'm sure that everyone in this workshop is very familiar with FDM, so I will just go through it quickly. FDM is composed of extremely light particles with a particle mass on the order of 10 to the minus 22 electron volt. So it's much lighter than the conventional CDM model. And because of such a small particle mass, its corresponding de Broglie wavelengths becomes kiloparsec scale, so on the astronomical scale. And because of that, it will show many wave-like properties, such as interference. So here I list 3 very good reference papers for the fuzzy dark matter. The governing equation of FDM is very simple. It's just this single particle Schrodinger Poisson equation. So psi is wave function, phi is the Newtonian gravitational potential, A is the cosmic expansion scale factor, and so h bar is 1 here. So one very important feature in this model is that it has only one free parameter, which is the m psi, the particle mass here. So one of the most important tasks in the study of FDM is to try to constrain this particle mass using different observations to test whether the estimated value of particle mass is consistent. So another important feature of fuzzy dark matter is that there is an effective quantum pressure that will suppress the small-scale structure. This feature can be mostly easily seen if you rewrite the Schrodinger Poisson equation into conservation laws, so just like the Euler equation in hydrodynamics. So this is the continuity equation, and the second equation is the moment equation. And this is how we convert the wave function to these fluid variables. So in comparison, this is the momentum equation in hydrodynamics. As you can see, the only difference between these two momentum equations is the first term on the right-hand side, which represents the pressure. So by rewriting this term in quantum fluid into a similar term in hydrodynamics, we can derive an expression for this quantum pressure, which is actually a stress tensor. And also note that this pressure is related to the spatial derivative of density, which will related to some aspect of the FDM simulations that I will talk about later. So this quantum pressure plays a very important role in fuzzy dark matter, because if we have pressure, we can define the corresponding Jeans length, which is the characteristic scale where gravity balance pressure. So above this scale, gravity dominates in both FDM and CDM. So we expect that these two models will behave very similar on scales larger than this Jeans scale. But what more interesting is for the scales smaller than this Jeans scale, because there the pressure will dominate, which will suppress the small scale structures. So for scales smaller or comparable to this Jeans scale, that's where we can distinguish the FDM and CDM. Okay, so this figure shows the large-scale structures. So for scales larger than the Jeans scale, between FDM and the CDM model. So these are cosmological simulations. As you can see, the large-scale structures predicted by these two models are very consistent. So the position of halos or these filaments are very similar. So these results are both expected and desirable, because as I just said, on large scales, we do not expect that these two models deviate from each other, because both of them, the evolution are dominated by gravity. But also, it's well known that the CDM model works very well on large scales. It's very consistent with observations on large scales. So we probably don't want to give any surprising results on these scales. But as I said, what more interesting is small scales smaller or comparable to this gene scale. So this figure shows a close-up of the density, just a slice of density distribution in our cosmological FDM simulations. Basically, we'll find these interference patterns everywhere. So from these filaments connecting different halos to these isotropic density perturbations, or sometimes we call it density granules, throughout the entire halo. Most importantly, in the center of each halo, we find this core, this bright region, and this is a core. This is very different from the conventional CDM model, which predicts that the central density profile is cuspy, so the density diverges at center, so the NFW profile. Here, for fuzzy dark matter, the density profile, it has a core profile, meaning that the density actually approaches a constant instead of diverge. So this figure shows the three-dimensional distribution of a simulation halo. So again, you see all these bubbles. These are the density granules in your FDM halo, and in the center you see this soliton. So this is the core I just mentioned, and this core can actually be fitted very well by this soliton solution. So soliton solution is just a spherical symmetric, non-dispersive ground state solution in the Schrödinger-Poisson equation. So very important questions we want to ask is, how does these density granules interact with the soliton? Or in other words, are there any connection between the halo and the soliton? Sometimes we call it core-halo relation. So I will talk about that in the next few slides. But first, yes.
Can I ask you a question?
Sure.
So as you said, there is the spherically symmetric soliton solution. To what extent is the soliton in the numerical simulation actually spherically symmetric? I'm just looking at the little picture there. It doesn't look completely spherically symmetric.
Yeah, it's never complete spherically symmetric. Yeah. But the fact that usually the spherical average profile can be fit very well by the soliton, meaning that it's kind of, I think it doesn't deviate from spherical symmetry too much. Yeah.
Okay.
Yeah.
Okay.
And later I will show you a movie about how this soliton actually evolved with time. There you will see more clearly that it's certainly not spherical symmetric. Yeah.
Okay.
Okay. So one feature I want to point out here is that you see these density granules and the central soliton actually share very similar characteristic scale. So this is just the de Broglie wavelengths corresponding to the temperature or velocity dispersion of this halo. So that's a very important feature in FDM halo. Okay, so about this core-halo relation. So the first question I want to ask is there a prominent core in every halo? So to address these questions, in 2014, we conduct a series of soliton merger simulation. And the answer to this question is yes. We always find a core in the center of every halo in our simulation. And moreover, as I just said, this core can be fitted very well by the soliton solution. So this figure shows the density profile. So each line corresponds to different halos, and data points are simulations. And this solid line is the soliton curve. Actually, in this room mean figure, you see the black data points are simulations, and the red curve is the analytical soliton curve. So they are very consistent with each other. So this is the typical halo density profile in FDM. So in the outer region, it's very similar to the NFW profile you can see here. But in the innermost region, you will have this soliton core. So density first arise and then approach a constant. So that's very different from both CDN and also other alternative dark matter models like warm dark matter or self-interacting dark matter. For this alternative dark matter model, usually they will also have core, but their core profile is very different from these solitons. Okay, so the next question we want to ask is, for a given halo, can we predict its core properties? In other words, whether there is a well-defined core-halo relation. So the answer is again yes. So this figure shows the core mass, MC, as a function of halo mass. Data points are our simulations, so different halos and at different redshifts. And this black dashed line gives a theoretical prediction. So we demonstrate from both numerical simulations and theoretical argument that this core mass should be proportional to halo mass to the 1/3 power with an additional redshift-dependent factor. Based on this relation, we can predict that, for example, for dwarf galaxies, they will have kiloparsec scale cores. There should be a minimum halos with a mass about 10 to the 8 solar mass. And Milky Way will also have a soliton, but it's more compact. Its radius about 300 parsec, and with a mass of about 10 to the 9 solar mass. And also, these solitons tend to be more compact at higher redshift because of this redshift-dependent factor.
Hsi-Yu,
yes.
By now, has this core halo relation been checked to much more massive halos?
Not in my understanding. I think because simulations is very challenging. So the most massive halo so far, I think different group get is about 10 to the 11. I think because their simulation box size is usually 1 to 2 megaparsec.
Right.
Yeah. So the total mass in such box is just not large enough to create the Milky Way. Yeah.
Okay.
Yeah.
Okay.
So as you just asked, actually many groups are addressing this core halo relation. And sometimes people get different results. So here I want to give my point of view about what may break the core halo relation. So for example, in an unrelaxed system, for example, systems just after major mergers, then certainly it will not obey this core halo relation. And for like non-isolated systems, like subhalos in host halo, because they will be affected by the gravity of host halo. For example, it may be tidal disrupted. Only the central soliton will survive. This is related to the soliton random motion that I will talk later. So for subhalos, it may also break these core halo relations. So in our simulations that I just show you, most of them are just isolated, relaxed systems. So for massive halos, like halos equal or above our Milky Way, or even gas cluster, it will also likely break the core halo relation because this isothermal assumption may become invalid. And of course, for systems with non-negligible baryon mass around the center or has a strong baryonic feedback around center, well, this will also likely affect the soliton properties. But finally, I want to emphasize that actually simulation resolution is also very important. For simulations with insufficient resolutions, it will also likely get results that deviate from this core halo relation. So I will give you an example shortly. Here I also list several references about this core halo relation. But this is likely not complete. So if your work is not listed here, just let me know. And I'm sorry about that. Okay, next I want to talk about simulations, the fuzzy dark matter simulations. So the challenges of FDM simulations lies in the fact that here we are simulating the evolution of wave function. So here I assume that you are solving the Poisson equation. So you can also solve this alternative fluid-like equation, but that's beyond the scope of this talk. So here we only focus on the algorithms that solve the wave function directly. So for this kind of algorithms, it's very challenging because you have to resolve all the features in this wave function. So here I give you an example. So this figure shows a slice of density distribution in our cosmological simulations. So you get several massive halos here. And for the black region, these are the low dense regions without any interesting feature. But this is density, which is wave function squared, so not wave function itself. So what does the wave function look like? So the corresponding wave function actually looks like this. So note that these two figures represent exactly the same slice in our simulation. But wave function shows much more complicated and interesting wave patterns, like ripples. The physical origin of these wave patterns is very simple because in quantum mechanics, we know that the velocity is inversely proportional to wavelengths. So when the materials here and here in these low-dense regions approaches these halos due to self-gravity, their velocity gets higher and higher, and so the corresponding wavelengths becomes shorter and shorter. So you see the wavelength is very long here and becomes shorter and shorter. Now, what does this figure tell us? It shows that this kind of FDM simulations require very high resolution to resolve all these wave features. For a conventional CDM simulation, you likely don't need to apply high resolution in these low-dense regions because the density is actually very smooth there, and density is both low and smooth. So it's relatively easy to properly capture the evolution in this low-dense region. But for fuzzy dark matter simulation, you still need adequate spatial and temporal resolution to properly resolve all these waves. And later, yes, please.
Just to clarify, the wave function plots, there are two sets of contour, one for the real and one for the imaginary parts.
This is just the real part. So I think like the red color probably is the positive, blue color is negative.
I see. I also see these purple contours, but those are also part of it. Okay.
Yeah. This is just real part. Yeah.
Okay.
So apparently, these kind of simulations require much higher resolution than the conventional CDM simulations, and that's why we also related to this gamma code we used for this fuzzy dark matter simulation that I will very briefly introduce in the next several slides. But here I want to first emphasize that simulation resolution is critical in FDM simulations. As a demonstration, here I show you two images. They are both projected dark matter density in cosmology simulations, exactly the same initial condition. The only difference is that the left figure is from a simulation with a relatively lower resolution. The right figure is from a higher resolution simulation. So you notice that in the left image with the lower resolution, these two halos are still on the way to merge. But in the higher resolution simulations, these two halos have merged already. So it means that structure evolution is delayed for simulation with insufficient resolution. And it's very important to keep in mind that if you only have one of these two figures, say you only conduct a lower resolution, it's likely that you won't notice any suspicious feature here because the halo looks normal, you get solitons, and everything looks fine. But only when you conduct this kind of numerical convergence test, you will see differences. And actually, I think you need more resolution. It's also possible that this higher resolution simulation is also wrong. Maybe you need even higher resolution. So it's very important to make sure that the numerical results converge. So that's my take-home message. So this is another example. So this shows the density profile of the same halo, but in two simulations with different resolution. So the halo mass is almost the same in these two curves. The blue curve is the lower resolution case. The orange curve is the higher resolution curve. But you see that first, for the results for simulation with lower resolution, the halo profile becomes steeper. Second, for the soliton, the lower resolution results give you a more massive soliton. So you still get the soliton, and I'm sure that this central profile can be fitted by a soliton profile very well, but you get a different soliton mass with the same halo mass. So, and again, if you only have one of these simulations, then you get, for example, you get this blue line, then it still looks like an NFI profile plus a soliton. So that can be very dangerous. So I hope these two figures give you some idea about the importance of achieving sufficient high resolution in fuzzy dark matter simulations. So the reason that why resolution is so critical here is that if your resolution is insufficient, then you cannot resolve the phase and density oscillation of wave function. And remember that the phase oscillation corresponding to the flow velocity, the density oscillation corresponds to the quantum pressure. So if you cannot resolve these oscillations, our simulation will likely to underestimate the flow velocity and quantum pressure. And so we get incorrect merger history and halo soliton profiles. That's also one of the reasons that so far fuzzy dark matter simulations are still, we can only conduct this kind of simulation in a very small co-moving box, like 1 or 2 megaparsec, much smaller than the CDN simulations. And I want to emphasize here that it's easy to make a soliton, as I just said, but it's more tricky and challenging to obtain a correct core-halo relation. And especially it's more challenging for more massive halos and for larger FDM particle mass, because that will require even higher resolution. So for insufficient resolution, because you underestimate the velocity and pressure, then they cannot counter gravity. So your halo will become too compact. So gravity will further contract the halo. So the gravitational potential becomes too deep. And because soliton is sampling this potential, so if the potential becomes too deep, the soliton will become too massive and compact. And so you will get a different core-halo relation. Especially your beta here will be larger than 1/3, as predicted in the previous slides. Okay, then I will very briefly introduce the gamma code, and then we will go to the soliton random motion. So first, the idea of this AMR, I think most of you are very familiar with this simulation technique. So basically, it allows your simulation resolution to adjust locally and automatically. So the resolution is no longer uniform. So which is very important for many astrophysical applications. So this movie is just showing colliding agent jets using gamma. So this is not fuzzy dark matter simulation. I just use it as an example. So gamma is a GPU-accelerated AMR code. So it supports many physics modules, of course, the fuzzy dark matter, and also many other common modules in standard astrophysical codes. It also supports many technical features. So I just listed here. And know that the gamma code is an open source, so you can download it directly in this link. But the fuzzy dark matter module has not been formally released yet, but it will be released soon. However, if you are interested in testing it, just send me an email. I will be very happy to share the code with you.
Hsi-Yu,
Yes?
In terms of resolution requirement, is it fair to say, as long as you are able to resolve the de Broglie wavelengths and the de Broglie locally, it should be okay? Is that roughly the requirement, or it has to be better than that?
I think that's the requirement. Yeah.
Okay.
Yeah, but it's a bit tricky to say correctly determine the local wavelengths.
Right.
Yeah. So the exact say refinement criteria in AMR is actually tricky.
I see. Yeah. In your AMR code, let's say, when people do n-body simulation or fluid dynamic simulation, AMR usually means the refinement is done in high density regions.
Yes.
Here, as you nicely explained, there's a lot of structure even away from high density region, even around void and so on.
Exactly.
And so is the AMR criteria where you have adaptive refinement? Is your criteria a little bit different from the usual ones?
Yeah, very different. We still need to resolve hidden region, but we also, as I said, we have to estimate the local wavelengths. So otherwise, as I said, the flow velocity will be underestimated, even in the low dense regions. So your halo mass accretion rate will be wrong. Yeah. Okay, so here I want to give you some idea of the performance of gamma because it's a GPU accelerated code. So these two figures shows the performance comparison between gamma and another MR code called Flash. So basically, gamma can achieve 2 orders of magnitude speed up compared to with Flash. This is not fuzzy dark simulation. This is for galaxy cluster merger simulation. But I just want to show you that one of the reasons we designed this gamma code is to exploit the GPU, the power of GPU to achieve such performance. Okay, now let's focus on the Soliton random walk. This movie shows the evolution of the Soliton. We are actually simulating the entire halo, but this movie only shows the central region. So the bright white region shows the Soliton. So as we discussed previously, first, it's certainly not spherically symmetric, right? Its shape constantly changes with time. And also, it's not only its density also change with time, its position also change with time. So it's kind of like a Brownian motion. It just move around. It will not leave the halo, so it will stay on the bottom of the halo, but it can kind of like randomly move on the bottom of the potential well. Okay, so this slide gives you a more quantitative result of this Soliton random motion. The left image figure shows the projected dark matter density at 4 different epochs. Here, this small blue dot gives you the central mass of the halo. So it is fixed. So we use it as a reference point. You see this Soliton shows this kind of confined random walk at the base of the halo potential. The right figure shows the offset between the Soliton and the halo. So normalized to the Soliton radius and as a function of time, which is also normalized to the characteristic oscillation period of Soliton. So you see that the separation between Soliton and halo is on the order of 1, so on the order of Soliton radius. And the characteristic time scale is also close to the Soliton itself. The different lines here represents different ways of defining the center because the definition of centers are not unique here. So to demonstrate numerical robustness here, we show you that our results are insensitive to the definition of centers. For example, here the Soliton center can be defined as the position of peak density or minimum potential. The halo center can be defined as the central mass of the entire halo or only the central mass of the high dense region. So no matter how you define the centers, so this Soliton random motion is there. Yeah. So next, we want to address this central star cluster in the dwarf galaxy called the Eridanus 2. The left figure shows the entire galaxy. The red dashed curve shows the half-life radius. The right figure shows the rooming of the central star cluster. The key questions we want to ask is, can this star cluster survive in an FDM halo? Especially, how does the Soliton random walk affect its survival? Okay, before showing you concrete results, let me briefly summarize the parameters of this system. So for the baryonic components, this Uranus 2 is an ultra-faint dwarf galaxy with a half-life radius of 0.3 kiloparsec, with an enclosed mass within this radius about 10 to the 7 solar mass, a very large mass-to-light ratio, a velocity dispersion of about 7 kilometer per second, and it has a galactic-centric distance of about 307 kiloparsec. And so it's moving toward us. It's moving toward the Milky Way, although it's still very far away now. For the central star cluster, it has a half-life radius of only 13 parsec. So it's much smaller than the radius of the galaxy. its luminosity is 2000, so its mass is about 2000 solar mass. So the mass is much smaller than the dwarf galaxy itself. Its age is estimated to be at least 3 gigayears. So this number is very important. So we will use this number to determine whether the star cluster can survive, whether it can survive or not in our simulations. For the dark matter component, we adopt a particle mass of about 10 to the minus 22 electron volt. A halo component has a real radius of 50 kiloparsec and the mass of 6 times 10 to the 9 solar mass. For the soliton, which is more important, it has a radius of about 0.7 kiloparsec and the enclosed mass about 10 to the 8 solar mass. So we pick these halos because this halos is quite consistent with the estimated enclosed mass of Uranus 2. As you can see, this radius is about twice larger than the half-life radius. So if we divide this number by factor of 2, then the enclosed mass should be divided by a factor of 8 because the density is constant. So then it becomes very consistent with the enclosed mass within this radius. So we pick up this radius, pick up this halo or soliton because its enclosed mass profile is consistent with Uranus 2. So the peak density is here, and it has a wave function oscillation period of about 100 megayear. So there'll be more details about our simulation setup. So we use this Gamma 2 code, and our simulation box covered the entire halo, and we model star cluster with the polymer sphere. So to properly resolve this star cluster, our spatial resolution needs to be very high. So even though we cover the entire halo, we increase the resolution in the innermost region to about 4 parsecs to properly resolve this star cluster with a very high temporal resolution and stellar mass resolution. And we demonstrate our numerical robustness by testing numerical convergence with different resolutions. And we also verified that the drift of this halo central mass is smaller than 1% of the soliton radius. So ideally, the central mass of halo is fixed because it's an isolated system. But because of numerical errors, it will still move around. But we demonstrate that it's smaller, much smaller than the characteristic, say, random walk distance in this system. Okay.
So you have how many stellar particles do you have? Something like that.
I think you can. It's like 2,000 solar mass divided by this number. Yeah.
Okay. Okay.
So in other words, each particle in our simulation does not present a single star. It's much smaller than that.
That's right.
Yeah. So this movie shows the soliton random motion, but here we put these black dots here is the star cluster. We put it at the center of the soliton at the beginning, and that evolved self-consistently. So first you notice that, okay, soliton just moved by itself. Soliton is much more massive than the star cluster, so it doesn't really care about the star cluster. So in that sense, the star cluster can be regarded as a tracer of the soliton. And because of this soliton random motion, there will be a characteristic separation between the star cluster and the soliton on the order of this soliton radius. Let me play it again. So you see the soliton just move around, the star cluster try to follow it, but it cannot really tightly follow it because soliton doesn't stay there. So there is a characteristic separation. And this separation will lead to tidal field because the star cluster will feel the tidal field from the soliton. And this simulation shows that this tidal field will disrupt the star cluster within about 1 gigayear. So here I show you the evolution of the stellar density profile. The black curve is the initial profile, just as a reference. The red curve shows the evolution. So you see the red curve drops very quickly because of this tidal disruption. So the star cluster, now after 1 gigayear, the density has dropped more than 1 order of magnitude. Okay. This slide shows you more quantitative results. So the left figure, the colors represent the stellar mass density. The contour are the soliton edge. So you see there's a separation between these two on the order of soliton radius. This is actually very important because the soliton density is flat in the inner region. So if star cluster lies within the soliton, it will get compressed because of this simple harmonic potential. If the star cluster lies outside the soliton, then soliton is just a point mass. So the tidal field will decrease with distance. So it means that the tidal stripping is most effective at the soliton edge. And that's exactly the star cluster locate, because the soliton random motion is also on the order of soliton radius. So, and also we can show that for star cluster located at the soliton edge, the tidal field from the soliton is comparable to the self-gravity of the star cluster, meaning that the star cluster is vulnerable to tidal disruption. So that's what we find in our simulations. The left figure shows the upper panel is the stellar density profile at 4 different epochs. The lower panel shows the enclosed stellar mass fraction as a function of time. So you see that so this purple curve is the reference soliton solution. Vertical curve is the half-life radius of the star cluster. So you see, this is the lower panel is the enclosed mass within this vertical line, and it decreases with time. So after, say, about 1 giga-year, the star cluster lost about 99% of its mass. And this 1 giga-year is shorter than the estimated minimum edge of the star cluster, which is 3 giga-year. So it seems to suggest that there is a crisis for fuzzy dark matter, because these simulations suggest that if the soliton indeed has this kind of random motion, then this star cluster cannot exist. It will be destroyed very quickly. To investigate this potential issue further, the next question we want to ask is whether this Milky Way tidal field can affect these results, whether it can affect the soliton random motion. So we conduct another set of simulations with very similar setup, except that now we add a Milky Way tidal field. And we assume a circular orbit of radius of 100 kiloparsec of irradiance 2. And we choose the simulation coordinate to move together with the dwarf gas with the irradiance 2. So in our simulation coordinate, the Milky Way is actually orbiting. So here are two movies. The left movie shows the entire halo. The right movie shows the rooming, the central region around the soliton. So you see the Milky Way is orbiting, and its tidal field will disrupt the halo of the irradiance 2. So the density surrounding the central soliton becomes smaller and smaller. However, the central soliton can survive. It remains intact. Okay. So here is more quantitative figures. So the left figure is the projected dark matter density at 4 different epochs. So the right figure shows the upper panel is the dark matter density profile, again, at 4 different times from initial condition to 4 giga-year. The lower panel shows the enclosed dark matter mass. So the mass profile normalized to the initial mass. So you see, within this soliton radius, the soliton remains very stable. But in the outer regions, the halo gets tidally disrupted within about a few giga-year. So we further find that without the interplay between halo and soliton, the amplitude of soliton random motion is significantly diminished. And because of that, the star cluster and soliton can coexist. This is demonstrated in this movie, which is again the evolution of the stellar density profile, but this time it's in a tidally stripped halo. So black curve is the initial profile, red curve is the evolution. So we show that the star cluster can survive longer than 5 giga-year, so longer than the minimum age of this star cluster, if the FDM halo has been tidally stripped by the Milky Way. So now it's 4 giga-year, so the star cluster remains stable. So now it's 5 giga-year. Okay. Now, so this figure shows the upper panel shows the offset between the soliton and halo. Again, it's normalized to the soliton radius, so as a function of time. So it shows that the soliton random motion becomes smaller over time as the halo being tidally stripped. So at the beginning, so this halo is still there. So the random motion, say the mean free path, is still on the order of soliton radius. But after about, say, 3 to 4 giga-year, the amplitude of soliton random motion has dropped by more than an order of magnitude. The lower,
so what you're saying here, if I want to make sure I understand correctly.
Yes.
The small the halo is being tidally stripped. So over time, when we talk about the halo, mostly is actually just the soliton itself.
Yeah. Yes.
And dominated by soliton, and from that point of view, it's not surprising the center of mass of the halo and the location of the soliton becomes very close to each other.
Right? Exactly. So at that part, there's no halo. Yeah. So what's more important is probably when the halo is partially disrupted. Okay. Yeah.
But I guess maybe it's a related question. As pointed out by Jens and also Dodi and company, the soliton oscillations could cause basically disruption of the cluster. I guess here, as you said, the random motion, the Brownian motion is diminished over time. I guess maybe the relevant question is, how about just the oscillation of the soliton itself, the density going up and down? Yeah, does that get diminished over time as well?
Not really. Yeah, that can still oscillate. So that's a very good question. But first of all, I think as pointed out in Dodi's paper, when they use the amplitude of soliton density, peak density oscillation, that gives you, I should say, that can be applied for FDM mass larger than, say, 10 to the minus 21. So here we are simulating 10 to the minus 22. So in this mass range, it's not ruled out by Dodi's paper. So yes, that's the first point. But it will be very interesting to check for more massive particle mass. In that case, even if the halo is disrupted, only soliton survive. But because of this, the soliton density oscillation, whether it will also, say, hit up the star cluster and destroy it. Mm-hmm. That's a related question, but it's not relevant here because of the particle mass range probe here.
Yes. Yeah. Yes. In your case, do you also see about 30% oscillation amplitude?
I would say oscillation amplitude is about a factor of 2. Say the peak density says 1, then occasionally it can go up to 2.
I see.
So on average, maybe it's like 0.5. So I think 0.3 is a reasonable value. Yeah.
I see.
But here, at least, we demonstrate that in this mass range, the soliton density oscillation will not heat up the star cluster efficiently. Yeah.
Right. Basically, in this mass range, I guess, basically the effect is adiabatic, no? The time scale of oscillation is actually longer than the dynamical time of the stellar cluster itself.
If we follow the argument in Dodi's paper, then yes. But we are also investing that, actually.
I see.
Yeah.
I see.
Okay, so this is actually the last slide. The lower panel shows you the enclosed stellar mass fraction as a function of time. So here we add the star cluster at 4 different times, the T0 here. So at the beginning, or 2 or 3 or 4 giga-year. So for example, the black curve means that we add the star cluster at the beginning of the simulation is here. For the green line, we add a star cluster here. So after the 3 giga-year, when the soliton random motion has dropped significantly. So it shows that the later the star cluster is added, the more stable it is. So it is expected because the random motion has reduced significantly. So if we add this cluster at 4 giga-year, which is the blue line here, then the star cluster becomes very stable throughout our simulation. So it's stable more than 5 giga-year. We stop our simulation at 9 giga-year. So it seems to provide a possible solution to the aforementioned FDM crisis. Yeah. Of course, there are many open questions. First, it's very important to obtain more accurate orbital parameters of Iridium 2. It has a very large uncertainty at this point. So our simulation only provides a proof of concept setup. So we assume a circular orbit and with the orbiting radius of 100 kiloparsec. But actually, this system at this point is almost 300 kiloparsec away. So it's unclear whether it is really on its second or third orbit around the Milky Way. If we can measure its proper motion more accurately, then we can answer this question. And if we find out that actually this system has never really entered our Milky Way, then the solution we suggested doesn't work at all. So you remain to be checked further. Other related questions about this Soliton random walk is that, for example, how does it depend on other parameters like FDM particle mass and halo mass? Because in this work, we stick with 10 to the minus 22 electron volt, and we also stick with a single halo that mimics the Iridium 2 system. So although the Soliton random motion, we find in our simulation has a similar time and length scale to the Soliton itself. So this seems to be quite natural, but it remains to be checked further whether it can be applied to when we change other parameters. And also for system with non-negligible baryonic mass, then of course the Soliton random motion may become much smaller. For example, in the Milky Way. Another important question is how does this Soliton random motion affect the observational predictions of fuzzy dark matter? So many previous work use Soliton to test FDM, to compare with different observations. But I think most of these works assume a static Soliton. So what happens if it starts to move around? So whether it will affect, for example, the dynamic friction and core stalling in dwarf galaxies, and how does it affect the galactic rotation curve, and how does it affect the estimation of the excess mass in the Milky Way center, like the central molecular rome, and whether it will have any impact on the black hole, on the supermassive black hole formation evolution. So I think there are many interesting questions we can address when we take into account this Soliton random motion. So here, let me summarize my talk here. The first take-home message is that the simulation resolution is critical in fuzzy dark matter. So it's very important to test numerical convergence carefully. So numerical convergence does not guarantee that you get correct results, but I think that's the minimum thing you have to do. Yeah, at least you have to verify it. For the Soliton random walk, which is caused by the Soliton halo interaction, in our simulation, it shows characteristic length and time scales close to the Soliton itself. And it may lead to a FDM crisis because the Soliton random walk can displace the central star cluster in the Iridium 2 system slightly outside the Soliton, which will lead to efficient tidal disruption of the star cluster. And we also propose a possible solution that the Milky Way tidal field may disrupt the halo of Iridium 2, but the Soliton can remain intact. In that case, without the interplay between Soliton and halo, the Soliton random motion is significantly diminished. And we demonstrate that in that case, the star cluster and the Soliton can coexist. Okay, thank you very much.
Thank you, Hsi-Yu. That was very nice, very nice.
Thank you.
Maybe since I asked a lot of questions already along the way, maybe just one further question. It has more to do with the first part of your talk about general simulation aspect.
Okay.
As you emphasize, the demand on resolution is such that so far it's only possible to run simulation with a fairly small box size. And I'm wondering, could you comment on this alternative method by, I think we might even hear a talk about it by Jens and Bodo and company, where it is some kind of a hybrid where on large scale, I think it's an n-body simulation.
Yeah.
N-body code, and then small scale is Ranger person. That should allow you to go to bigger box sizes now.
I think that will help, because in the smooth component, I think it's reasonable to use this fluid approach.
Right.
So some company use this fluid approach everywhere. So that could be problematic. So I think in a paper by Brownian, right, and so showing that in the nonlinear regime, when you have say void, your density close to 0, then this fluid approach may break. We actually find that long time ago, and that's one of the reasons we haven't really switched to that fluid approach. But I agree that in this kind of hybrid scheme, it can improve. But how much it can improve, I'm not sure, because you still need very high resolution to resolve the entire halo, and that's the most expensive part. You have this zero density everywhere, and the work wavelength in the entire halo is roughly the same. It means that you not only need to resolve the soliton, you have to resolve the entire halo with approximately the same high resolution. So that is actually the most expensive part. Yeah. So so it can help. Hybrid approach can help, but I don't know how much it can help actually.
So we are still very far from being able to simulate an actual galaxy cluster, for example.
Gas cluster is too difficult, and even for Milky Way, so 10 to the 12 solar mass.
Yeah.
That's also very challenging. I don't see any group has done that.
Right.
Yeah, it's possible to, I think, to adopt this hybrid approach with the zooming simulation to capture a single Milky Way-like halo. I think that's probably doable, but already very challenging. Yeah.
Okay. Very good. Thank you, Hsi-Yu.
Oh, thank you for asking so many good questions.
This was very nice, super nice. Thank you.
Okay, so let me, I will stop the recording.